What actually happens when you press a button on a machine and it just works? What's the hidden logic behind bottling lines, elevators, or conveyor belts? And more importantly, can you learn how to build that logic, even if you've never programmed a machine before? Today, we're diving into the world of PLCs, or Programmable Logic Controllers, the digital brain behind everything from packaging machines to automated assembly lines. By the end of this video, you'll know what a PLC is and how it works, how to connect inputs and outputs, and how to write your first working program from scratch. Do you want answers? Watch the full video to get them. A PLC, or Programmable Logic Controller, is the unseen brain behind countless machines in industrial automation. Unlike a regular computer, which you might use for browsing or spreadsheets, a PLC is designed for one thing: controlling machines and processes in real time, with speed, consistency, and absolute reliability. These devices are used everywhere, from food factories to car plants, packaging lines to traffic systems. If a machine follows a logical sequence, like starting a motor when a button is pressed or stopping a conveyor when a sensor detects an object, a PLC is likely the system making that decision. What sets a PLC apart is its purpose-built architecture. It's engineered to handle rugged environments, electrical noise, and constant operation. It doesn't crash, it doesn't overheat, and it doesn't need an operating system like Windows to function. Once you load a logic program into a PLC, it cycles through the same instructions thousands of times per second, reading inputs, executing the logic, and updating outputs. Let's say you press a button on a control panel. That signal is received by the PLC through an input. The PLC checks what your program tells it to do. Perhaps it needs to start a pump or open a valve. If so, it sends a signal through its output terminals to make that happen. No mouse clicks, no apps, just pure logic, executed with perfect timing. PLCs are trusted in automation because they're built to be reliable and fast. They're used in systems that cannot afford delays or failure: bottling machines that process hundreds of drinks per minute, robotic arms that weld with millimetric precision, or packaging lines where 1 second of downtime costs thousands. In other words, a PLC isn't just another device. It's the invisible logic system that turns electrical signals into coordinated, repeatable actions. And learning how to program one means you're stepping directly into the world that keeps modern industry running. So now that we know what a PLC does, let's break down what it's actually made of and how it connects to the physical world. At its core, a PLC is a modular system made up of key hardware components, each designed for a specific task. The most important part is the CPU, or Central Processing Unit. This is the brain of the system, the part that runs your logic program and controls everything else. It's where all decisions are made based on the inputs it reads and the logic you've written. Next, you have input and output modules. Inputs are how the PLC receives information. Things like push buttons, proximity sensors, limit switches, or level detectors. These tell the PLC what's happening in the real world. Outputs, on the other hand, are how the PLC sends commands. That could mean turning on a light, starting a motor, opening a solenoid valve, or triggering an alarm. Most PLCs also have a power supply module that converts the incoming voltage, usually 24V DC or 230V AC, into the level the system needs to operate. Some setups also include analog modules for reading and sending variable signals like temperature, pressure, or flow rates. And then there are communication ports. These allow the PLC to talk to other devices, like HMIs, human-machine interfaces, other PLCs, or industrial networks like Ethernet, IP, or Profinet. This is how you build larger systems that work together, whether it's an assembly line, a bottling plant, or a fully automated warehouse. If you were to wire a simple PLC project yourself, you might connect a push button to an input terminal, a light bulb to an output terminal, and power everything with a 24V power supply. Once you load your program into the CPU, pressing that button could turn on the light instantly. No magic, just logic. That's how every major automated process begins, with clean, consistent hardware. Simple components connected in the right way waiting for your code to bring them to life. Once your hardware is connected, the next step is programming the PLC, and that's where specialized software comes into play. Unlike traditional coding, where you might use Python or JavaScript, PLCs are programmed using environments tailored for industrial logic. The most common tools vary depending on the manufacturer. Siemens uses TIA Portal. Allen Bradley systems run on RS Logix or the Studio 5000, and many other platforms rely on CodeCs, a universal development environment used by a wide range of PLC brands. Each of these environments has a similar workflow. You connect your computer to the PLC, usually over USB or Ethernet, launch the software, create a new project, and select your PLC model. Once the project is set up, you can begin writing the logic that tells your machine what to do. Here's where the IEC 61131 standard comes in. This international standard defines the programming languages used for PLCs. The most widely used is ladder diagram, LD, which visually resembles the electrical relay diagrams used by electricians, making it intuitive, especially for those with a wiring or maintenance background. Another option is structured text, ST, a text-based language similar to Pascal or C. It's powerful for handling more complex tasks like math operations, loops, or conditional logic. Then there's function block diagram, FBD, where logic is built using visual blocks that represent operations, ideal for visual learners or process engineers. Most modern PLC software allows you to mix and match these languages within the same project. That means you can use ladder logic for simple tasks like turning on a motor, and structured text for more advanced sequences or calculations. The user interface is built for clarity. You can monitor live inputs and outputs, test logic in simulation mode, and even troubleshoot programs while the machine is running, something you don't get with the most general-purpose coding environments. So whether you're writing your first button turns on light program, or developing a sequence for a multi-stage packaging system, the software tools are designed to help you focus on logic, not syntax. And the best part? Once you understand how to build one program, you can scale up to more complex systems without changing platforms. Now it's time to put everything together and write your very first PLC program. And to start, we're going with the classic. Press a button, turn on a light. It may sound simple, but this example teaches the foundation of how every industrial control system works. One input, one output, and a clear logical connection between them. In ladder logic, the program looks like a horizontal rung, just like a rung on a ladder. On the left side, you place a normally open, no contact. This represents your input, in this case, a physical button. On the right, you place a coil symbol, which represents your output, the light you want to activate. When the button is pressed, the contact closes, allowing power to flow across the rung and energize the coil. In real terms, that means the PLC receives the signal from the input, processes the logic you've written, and sends a signal out to turn on the light. But what makes this really interesting is the scan cycle. Every PLC follows a 3-step cycle. Read inputs, it checks the status of every sensor, button, or switch. Execute the logic, it runs your ladder diagram from top to bottom. Update outputs, it turns on or off anything connected to the output terminals. This cycle happens in milliseconds, so fast you'd never notice a delay, but consistent enough to rely on in a factory with thousands of actions per minute. Most PLC programming environments come with a simulation tool. You can build this exact program on your PC, press a virtual button on screen, and watch the light turn on, no hardware needed. And when you're ready, you can transfer that exact same logic to a real-world setup. This may seem basic, but it's the foundation of everything more complex. Start-stop logic, motor control, safety interlocks, even advanced robotics. It all starts with understanding how an input triggers an output, and how the PLC carries that message instantly every time. Let's take your basic logic one step further. What if you don't want the light to turn on immediately when the button is pressed, but only after a few seconds? That's where timers come in. In ladder logic, you'll use a function block called ton. which stands for On Delay Timer. It's a standard instruction across almost every PLC platform. Here's how it works. The button still acts as your trigger. But instead of turning on the light directly, it starts a timer. Once the timer reaches its preset delay, say 3 seconds, the output, your light, turns on. In ladder logic, you'll see the TON block with 3 key values. In, the input condition, the button being pressed. PT, the preset time, how long to wait. Q, the output, what gets activated after the delay. So now the PLC still reads inputs, runs the logic, and updates outputs, but it's also tracking time within the program. You've just added sequencing, one of the core skills in a real-world automation. These kinds of logic blocks are everywhere in industry. Delays before motor start, timed water valves in bottling plants, light indicators in packaging lines, controlled activation of robots after a safety check. And it all builds from that one idea, an input, a condition, and a timed output. So let's wrap it up. You now know what a PLC is, what it does, and how it fits into the industrial world. You've seen the basic hardware, explored the software, and built your first program, from a simple button and light to a functional timer. If you can follow this, you can start writing real automation logic. You're no longer just watching machines. You're starting to understand how to control them. But this is just the beginning. If you found this video helpful, hit the like button and subscribe for more hands-on guides, real-world automation breakdowns, and deep dives into industrial tech. Leave a comment if you're stuck on something or want to request the next tutorial. And don't forget to check out the next episode, Top 5 Mistakes in PLC Programming and How to Avoid Them. This video is produced by Autom8, the platform connecting robot and PLC programmers with businesses building the future of smart manufacturing. Visit autom8deal.com to stay ahead in the world of industrial automation.